The Bohr model, proposed in 1913 by Niels Bohr, revolutionized our understanding of atomic structure. This presentation will explore the key concepts of the Bohr model, its strengths, and its eventual limitations. Rutherford's model accurately described the existence of a dense, positively charged nucleus but failed to explain the stability of atoms and the emission of specific spectral lines. Bohr's breakthrough addressed these shortcomings by proposing a model where electrons orbit the nucleus in quantized energy levels, explaining both stability and spectral lines. Bohr's postulates include quantized energy levels where electrons exist in specific energy levels around the nucleus, stationary orbits where electrons in specific energy levels don't radiate energy, and electron transitions where electrons can jump between energy levels by absorbing or emitting photons of specific energy. Bohr proposed that electrons move in circular orbits around the nucleus. The angular momentum of an electron in a stable orbit is quantized, meaning it can only take on specific discrete values. This quantization leads to a formula that relates the electron's angular momentum to its orbit's radius and energy level. When an atom absorbs energy, an electron jumps to a higher energy level. When the electron falls back to a lower energy level, it emits a photon of specific energy, corresponding to a spectral line. The distinct spectral lines observed in the emission spectrum of an element provide evidence for the quantized nature of energy levels. The Bohr model was most successful in explaining the spectrum of the hydrogen atom, which has only one electron. The model correctly predicted the energy levels of the hydrogen atom, which are quantized and correspond to specific spectral lines. Bohr's explanation of the spectral lines in the hydrogen atom provided strong support for its validity. The Bohr model was most successful in explaining the spectrum of the hydrogen atom, which has only one electron. The model correctly predicted the energy levels of the hydrogen atom, which are quantized and correspond to specific spectral lines. Bohr's explanation of the spectral lines in the hydrogen atom provided strong support for its validity. The Bohr model failed to accurately predict the spectra of atoms with multiple electrons and relied heavily on classical physics, which is not always applicable at the atomic level. Additionally, the model could not explain the wave-like nature of electrons or their probability distributions in space. Despite its limitations, the Bohr model was a significant step forward in understanding atomic structure and paved the way for more sophisticated quantum models. The development of quantum mechanics revolutionized atomic theory, providing a more accurate and comprehensive description of atomic behavior. The quest to understand the atom continues, with new discoveries and advancements constantly shaping our understanding of this fundamental building block of matter.